Hi, I'm Mary Brady, and this is Lab 4 on magnetic braking with Faraday's Law. The purpose of this lab is to model Faraday's Law experimentally and computationally through observing a magnet falling through a tube of aluminum foil and using a glow script model. The magnet fell slower due to induced magnetic field from change in flux, and the assumptions are that there are no air resistance, the north end is pointing down, and the tube is made of a non-ferrous material, so the magnet isn't influenced by its magnetic field. Faraday's law and Lenz's law. So voltage is created from the negative time derivative of change in magnetic flux. The negative sign is Lenz's law, which states that nature abhors a change in magnetic flux. And the Biot-Savart law, to calculate magnetic field. And Newton's third law, reciprocity. Newton's second law, force equals mass times acceleration. Magnetic flux, which is that the dot product of magnetic field and the n hat times the area, or change in area. And then Ohm's law, EMF is equal to current times resistivity, and magnetic force on a wire loop, force is equal to current cross product of external magnetic field. And here is a force diagram. This is the tube. This is the magnet. The magnetic force from the induced current is pointing up against the magnet in the opposite direction of gravity, but gravity has a larger magnitude, so it points down and it falls down. Here are my initial conditions. The system is the bar magnet. Surroundings are the tube of aluminum foil and the earth. Here is my measurements for the time it took for it to fall and the length of the tube. All right, here's my physical constants I used, and I used my initial conditions to set up the aluminum foil, and I had gravity in the negative y direction as mass times g. Here's my mu mag from lab 3, and I also use my lab 3 code to write and find the magnetic field. I use the magnetic field to find the change in magnetic flux, or dF dt, and 4 pi is coming from, and the 5 halves is all coming from taking the derivative of the change in magnetic flux, which is magnetic field times area. And then the current is the negative flux over resistivity, and the flux, or change in flux, is the EMF. And that's Ohm's law. And I found the magnetic force acting on the ring by 2 pi times ring radius, which is the change in length, times the ring current, times the external B field, times sine theta between them. So this is the cross product. And then I found F net as magnetic force plus gravitational force. This is all acting on the magnet. And then I used Newton's second law to find the velocity update formula and position update formula. The counterclockwise is the red, and this is pointing down, and the blue is the clockwise current working upwards. This is what's slowing down the magnet, and if I were to flip it, it would go, it would be flipped. The colors would be flipped. My end results were that there was a difference of 0.074 seconds between my experimental and my computational data, and this is because I changed my mu. My original mu made the computational model run for only 0.25 seconds, so I assumed I made an error in lab 3. So I changed my mu until it was more realistic. This means there was an error, and the timestamps on my camera roll also rounded to whole numbers, so I couldn't find an exact decimal, so that could also have influenced the difference between my experimental and computational data. If the resistivity was reduced, the value for current would be larger due to Ohm's law, and if the induced current was larger, the magnitude of the magnetic force from the loop would be larger, making the magnet fall even slower. If there were holes and slots, the model would have less rings, and less rings means that the induced current would be smaller. So the magnetic force pushing up against the falling magnet would be smaller. As a result, the magnet would fall much faster and even closer to if there was no tube around it. That's all. Thank you for watching.